mention here that my research work was initially supervised by Professor Maurizio Penco. Unfortunately, he passed away on 14th of December 2011. And since then, Professor Fabio Binotti and Professor Luciana Sartorio were guiding my research activities in the last year of my PhD. And I'd like to express my sincere gratitude to them for their cordial cooperation. As you can understand from the title of my presentation, that the whole research work is concerned with the development of self-healing materials. So at the beginning of the presentation, I'd like to introduce you to the key concept of the whole research work, which is self-healing. And in the following parts of the presentation, I'd like to take you some crucial experimental parts and some important results that I obtained in the last 3 years of my PhD. So what is self-healing? Self-healing is a biomimetic concept because this is a unique feature in any biological system around us. So self-healing in any biological system can be defined as a complex and dynamic process which consists of different biochemical and biophysical activities in order to restore any structural damage in the system. And scientists have always been interested to replicate such idea in order to develop some artificial system with healing ability. So the ideal definition of a self-healing material could be that as any material that has the inbuilt capacity to heal any kind of damages without any external interventions. And over the past 2 decades, there have been a lot of research works in the scientific community to develop such materials with healing ability. For example, here you can see that Professor Scott White in 2001 first published a work where they wanted to mimic the wound healing mechanism of human bone tissue to develop an epoxy-based composites, where they actually embedded microcapsules containing healing agents and dispersed the catalyst inside the matrix. Upon crack initiation, if the crack also breaks the microcapsule, it will release the healing agent, and when it comes in contact with the catalyst, it will initiate the polymerization at the crack, and this way they self-heal. Another interesting example could be the work done by Professor Jan Bond in University of Bristol. They actually tried to mimic the plant vasculature in order to develop a composite laminates, where they embedded hollow glass fiber containing healing agents inside, and upon crack propagation, the healing agents will be released from the hollow glass fiber, and thus they will self-heal. Another interesting approach was developed by Professor Tuki et al., and they actually tried to mimic the vasculature in skin, which is the blood vascles under the lower epidermis of our skin. And they tried to mimic these network of blood vessels inside a composites by embedding a three-dimensional network of hollow glass fiber in the composites. And upon crack initiation, due to the internal pressure difference, the healing agents will go to the crack and heal the crack. These are very promising extrinsic type of self-healing materials. However, because of their very expensive synthetic route, they are still not very technologically convenient. There is another class of self-healing material which is ballistic self-healing materials, and I am working on ballistic self-healing materials. Ballistic self-healing materials are a class of materials that can heal very high energy impact damage. And this kind of self-healing materials can have very important applications, like they can be used to maintain the pressurized atmosphere in aircraft or spacecraft, or they can be used as self-healable window in a space shuttle, and so on. The first research work on ballistic damage-initiated self-healing in polymer was reported by Stephen Callista in 2007. He actually studied the self-healing behavior in ionomer, and he proposed that the self-healing in ionomer is actually the function of melt elastic recovery at the impact zone, and a complete interdiffusion phenomena at the impact zone lead to the complete self-healing of the sample. After that, there has been a very few work to develop such self-healing material. For example, some efforts have been devoted to develop a self-healing material based on polydimethyl siloxane, where the two different types of microcapsules containing healing agents were embedded inside the laminates of polydimethyl siloxanes, and this kind of material exhibited self-healing behavior at very low energy impact damage. However, there is still a search for a very technologically convenient approach to develop self-healing materials in order to overcome the technological limitation in the present industries. So I started working on polymer blending in order order to develop self-healing materials. This was my first motivation. As we all know that polymer blending is very useful to develop some new materials where you can blend 2 or 3 polymers to have a wide range of properties in the final material. And the second motivation was to identify different parameters that can affect the self-healing behavior of the pure component as well as in the blend. And in order to do this, I started studying the self-healing behavior in the single component system, which is the pure polymers. I studied the self-healing behavior in ionomer, which is the polyethylene methacrylic acid copolymer, and functional elastomers. And after understanding the self-healing behavior in the single component system, I moved toward to the multi-component system, where I studied the self-healing behavior in blends, ionomer with elastomers and ionomer with the semi-crystalline polymer. Before going into the detail about the results that I obtained in different systems, I'd like to give you an overview of some important experimental thoughts that was crucial to identify the healing ability of the material and the healing on. I have a manometer. If the sample can maintain a pressure difference of 0.8 bar at the impact zone, it means the hole is closed, and that gives indication about the healing of the damaged zone. If I observe a immediate pressure decay, it means the hole is not closed, so the material was failed to self-heal. The second setup consists of a gas cylinder, a standard pressure vessel, a water beaker containing water. And in the second setup, I have a manometer where I can use a different pressure difference to identify the healing efficiency of the material. And each apparatus in this setup was connected through a rubber tube. And since the basement of the standard pressure vessel is circular, I have to prepare circular sample from the rectangular sample, and then the circular plate was inserted at the bottom of the standard pressure vessel, and it was closed with the upper part of the vessel. And then the sample here was exposed to a pressure difference for a certain period of time. If the damaged zone is not completely closed, I would see a water bubble immediately in the water beaker. But if it does not show the evidence of a water bubble in the beaker, it means the sample is self-healed. So these two setups were very important to identify the healing ability and healing efficiency in each sample. Now I'd like to go through some important results in each system. At the beginning, I started studying the ballistic self-healing in ionomers. I should mention here that ionomers are random copolymer that contain both polyethylene and methacrylic acid content, where the methacrylic acid content is usually 15 weight %, and this acid is partially neutralized by the trace metal ion like sodium, potassium, or quaternary ammonium ions. So I studied 2 different ionomers, polyethylene methacrylic acid containing both sodium ion and zinc ion. At the beginning, I studied their chemical structure by FTI analysis. I observed both the ionic aggregates and the carboxylic acid groups. And I should mention here that the ionic aggregates are very important for the promising thermal and mechanical behavior of ionomers. I also studied their ballistic self-healing behavior. And in the ballistic self-healing evaluation test, both of them showed self-healing as it was expected. As it was proposed by Stephen Callista that during the bullet penetration at the impact zone, there is a temperature rise at the damaged zone, which is about 110 degrees Celsius. And in my DSC study, I found that this is actually 15 to 20 degrees Celsius above the melting point of pure copolymer. And if you take a closer look at the impact zone of both ionomer, although their morphology is different, but you can see a complete interdiffusion and melt flow behavior at the impact zone, which is further supported by thermally activated hydrogen bonding that lead to a complete self-healing in the impact zone. I try to study further how to evaluate the self-healing ability of ionomer, and I try to investigate what physical parameters can limit their self-healing ability. In these micrographs, you can see that the ballistic self-healing of ionomer was tested when the bullet speed was 2 km per second. The material showed self-healing. But if we material did not show show the self-healing. That means that there are some physical parameters such as the size and shape of the bullet or velocity of the bullet that also affect significantly the self-healing ability of iron ore. I also studied the self-healing behavior in rubber, in epoxidized natural rubber. Since this work is concerned with the self-healing in elastomer, at first I would like to give you some interesting information on the self-healing elastomer. The first self-healing elastomer was developed by Professor Ludwig Liebler in 2007, and he actually developed a hydrogen bonded resin using different dimerized fatty acid, as you can see here. And he actually developed a dynamic supramolecular approach to synthesize the supramolecular self-healing rubber, where it contains multivalent hydrogen bonding, and which are individually weak but collectively can have a high load bearing capacity, as you can see the stress strain curve of this pure rubber. And they studied the self-healing behavior by cutting the sample in the middle and then putting it together just by pushing by hand. And after 180 minutes, the sample showed 90% recovery of its purging strength. Another research work by Professor Guan was recently done to develop a multiphasic thermoplastic self-healing elastomer, where they actually developed this elastomer using polystyrene as a hard domains and polyacrylamide as a soft domain. And due to the presence of hydrogen bonding in the material, it shows a supramolecular self-assembly that lead to the self-healing of cut damage in the sample. And they studied in the same manner the self-healing behavior of the rubber by cutting in the middle, and after a certain period of time, they found that the material can recover almost 80% of its virgin strength. However, I should inform you that most of the work on self-healing elastomer was done using the supramolecular chemistry, but no work has ever been reported on the self-healing behavior of conventionally synthesized elastomer. And this is why I studied the self-healing behavior of epoxidized natural rubber. Since the epoxidized natural rubber at room temperature is very sticky in nature, I tried to understand their addition behavior. And to do that, I performed the pill test, which is a conventional way to understand the addition strength in the rubber. You can see the generalized sketch of the pill specimen. And the pill test was done in T-pill geometry. This is the typical pill record that I obtained from the pill test. And pill strength was calculated from this pill curve. Well, this slide presents the pill strength of rubbers. I should mention here that pill specimens were treated at two different temperatures, at 25 degrees Celsius and at 60 degrees Celsius for different period of time. So the pill strength reported here is a function of time and temperature. As you can see, at 25 degrees Celsius, the highest pill strength was exhibited by ENR 50. And when I treated the sample at 60 degrees Celsius, the material show higher pill strength than the material treated at 25 degrees Celsius. And you can see that the pill strength of ENR 50 is absent here. This is because when we treated the sample, for example, ENR 25 sample having 25 mole % of epoxidation, I treated the sample for 30 minutes at 60 degrees Celsius. And in the peeling test, this is the typical peel record for ENR 25. But at the same condition, the ENR 50 showed a different peel record, which is more like the stress strain curve for about ENR 50 sample. And this behavior can be ascribed to the complete cohesion at the interface of the peel sample. And this strong cohesion is not only supported by the interdiffusion of the sample, but also the interaction among polar groups can play a significant role. I should mention here that I did not synthesize the epoxidized natural rubber in the laboratory. This was a commercial epoxidized natural rubber. But in the literature study, I found that during the epoxidation of rubber, due to the high concentration of the acid, or very low pH, or very high temperature, or even if the synthetic route is very long, it gives the epoxide ring opening products, which can be identified in the sample by the presence of hydroxyl group, carboxyl group, or ethyl group. And in the FTR analysis of my sample, I found that in the FTR spectra of ENR50, it shows the presence of some polar groups like hydroxyl group, carboxyl group, ethyl groups, and also the epoxy group. And this gives further indication about the importance of having higher mole percent epoxidation and also the presence of polar group that can lead to the higher Phillips strength in the ENR50. I also studied their self-healing behavior in ballistic test condition, and in the ballistic test condition, I found that only ENR50 having 50 mole percent epoxidation level showed complete self-healing behavior. And if you take a closer look at the impact zone of ENR50, it shows a complete interdiffusion at the impact zone. Since this interdiffusion behavior is largely influenced by the mobility of macromolecular segments in rubber, I tried to understand the effect of the crosslink density of rubber on their self-healing. So I vulcanized the rubber with different amount of dicumene peroxide. As you can see in this plot, the crosslink density of rubber is a function of dicumene peroxide content. As we increase the dicumene peroxide content, the crosslink density increased. And in the ballistic ionomer blends, I actually studied two different kinds of ionomer blends, ionomer with elastomers and ionomer with a semi-crystalline polymer. The strategy was to verify the effect of both phases, the ionomer phase and rubber phase. In ionomer phase, the variables were the copolymer that does not contain any ion, which means the acid content is not partially neutralized, and then I used sodium and zinc, which are monovalent and divalent cation in the ionomer phase. And in the rubber phase, I tried to observe the effect of different epoxidation level. And in the final product, of course, we have a wide range of thermal and mechanical properties with different level of healing efficiency. At first, I studied the pure copolymer and ionomer and epoxidized natural rubber 50 blends. And you can see that in the pressurized airflow test, all the compositions showed self-healing behavior, irrespective to their processing conditions. And in the sodium and rubber blends, also in this case, I observed complete self-healing with high healing efficiency at each compositions of the blend. However, when I blended zinc ionomer with epoxidized natural rubber